Hello and welcome to this new tutorial, the second big step of this implementation. We have already created one brain, the brain of the generator, and now we're about to create the second brain of our deep convolutional GANs. I'm talking of course about the brain of the discriminator. And we're going to proceed exactly the same way as we proceeded for the generator. We're first going to define a class that will define the architecture of the neural network for the discriminator. Then this class will also include a forward function to forward propagate the signal inside this new neural network. And then once the class is made, we'll create a discriminator object, that is, we'll create the brain of the discriminator. So let's do this. Let's tackle the second big step of our deep convolutional GANs. So we are starting with class, of course. Then we need to give a name to this new class that will define the discriminator. And since we called the class of our generator G, we're going to call this one D. I think that makes sense. And so D, again, is going to inherit from the NN module. And so inside, we use again NN.module. All right, then colon, and then we go inside the class to start with the init function that will define the architecture of the neural network. So that's the same. We start with def, and then double underscore, init, double underscore again, and some parentheses. And inside we only input self, which will refer to the future instances of our class that will be created, that is, the object, and that will allow us to associate the specific variables that are attached to the object. That is, I'm talking about the properties of the object. The object will be the neural network of the discriminator, so these properties and variables will be the different modules composing the architecture of the discriminator. Alright, so now, colon, we go inside the function, and same, we start by activating the inheritance using the super function, which takes as argument our discriminator class and our object self. Then don't forget, we add a dot here, double underscore, init, double underscore again, and some parentheses. Perfect, inheritance activated. Alright, and now things are going to get interesting. I'm going to try to make you guess what we're going to start with. We have to start with the first module of this architecture of the neural network of the discriminator. And so according to you, what is going to be this first module? Is it going to be an inverse convolution like before? Or is it going to be a convolution? Or is it going to be a full connection? Well, think about this for a second. And until then, I will get my main, again, which represents the meta module that will contain the different modules composing the architecture of the neural network. So exactly like before. So self.main, and this module will be a big sequence of layers, that is a big sequence of modules, and therefore I'm setting this main meta module to be an object of the nn.sequential class, parentheses. And here we go. Let's see if you got this right for this first module of this architecture. Let's see. All right, so to answer this question right, well, we need to understand what the discriminator is going to do. It's going to take as input a generated image coming from the generator and return as output a discriminating number, which will be a value between 0 and 1. Therefore, since it takes as input a generated image, the generated image created by the generator, well, that means it takes as input an image, and therefore the first module of our architecture is simply going to be a convolution. Not an inverse convolution, that's only for the generator, but this time a convolution. It's going to take as input an image created by the generator, and through the convolution, and then of course some more convolutions, we will get in the end a simple vector of one element that will contain the discriminating number, a value between 0 and 1. So there we go, you have the idea, and now it's going to be the same as before. We're going to add a series of different convolutions with different parameters, and we'll batch norm the feature maps, and of course we'll apply some rectifications. I will let you find out about some surprise regarding the rectification. It's not going to be a ReLU, it's going to be something a little more sophisticated. We will see that in 1 or 2 minutes. But let's start with our first module, that is our convolution. So to get this first module, we're going to create an object of the conv2D class, and therefore I'm taking my NN module, dot, and then I'm getting the conv2D class. Here it is, perfect, very easy. Now, something less easy, the parameters of this conv2D class. So it's actually not that hard, and I'm going to give you something else to get. What do you think is going to be the parameter we have to input here for the first argument of this conv2D class? Remember, that corresponds to in channels, that is, the dimensions of the input. So, as we just said, the input of our discriminator, and therefore of this first module that is the convolution, is an image created by the generator. So to answer the question, what is going to be the input of this first convolution, we simply need to look at the output of the generator. And the output of the generator, remember, is these 3 channels here of the image. So the input of our discriminator is nothing else than 3. The 3 channels of the generated image created by the generator. Perfect? And then it's going to be the same. We're going to specify a number of feature maps, a kernel size, a stride, a padding, and choosing true or false for the bias. So here we go, let's do it. We're going to choose 64 feature maps, then a size of 4 for the kernels. So these are going to be squares of size 4 by 4, then a stride of 2, and a padding of 1. And eventually, last but not least, we choose to have no bias, and therefore, like before, I'm choosing bias equals false. Alright, first module done, congratulations. Now, second module. What do you think the second, operation is going to be? We're not going to apply a batch norm yet. We will do that for the next convolution. However, we always need to apply rectification. And that's the surprise I wanted to keep from you, but I'll tell you it right now. We're not going to use a rectifier activation function. We're not going to use a ReLU function. We're going to use a leaky ReLU. So what I'm going to do now, I'm going to go to Google. Here is Google, and here is the leaky ReLU. The leaky ReLU is very close to the ReLU, but besides having the max of 0 and x, which actually is the formula for the ReLU, we have this addition of the negative slope multiplied by the min of 0 and x. So that's a slight change in the formula, and if you put that into a graph, you can see the difference. The ReLU is a horizontal line equal to 0 here for the negative values of x, and then the straight line y equals x. But for the leaky ReLU, we have this slight change here, which gives some negative values for the negative values of x. So that's the slight difference. I thought it was good to show you this. And now, why do we choose to use a leaky ReLU instead of a ReLU? Well, again, that's an artist's job. It comes from experimentation and research. Basically, for the convolutions of the discriminator, it works better with the leaky ReLU than a simple ReLU. So I'm getting back to Python, and therefore, if you all agree with the leaky ReLU, let's apply a leaky ReLU. So to apply a leaky ReLU, we take our NN module, and then dot, and then we will find very easily the leaky ReLU. Here it is, and we need to input several arguments. Of course, the negative slope, and we'll choose not 0.01, but 0.2. Again, a value chosen from experimentation and research. So 0.2, and then we have a second argument in place equals false, but we'll not set the value of in place to false, we'll set it to true. Again, if we go back to the PyTorch documentation, by the way, yes, this is the PyTorch documentation that I highly recommend to go through while watching the tutorials, or even anytime. That's a great documentation, it's very clear. And so if we look at this second argument in place, well, you can see that's an argument that, if set to true, can optionally do the operation in place. The default value is false, but we chose to set it to true to benefit from this option. Alright, So let's go back to Python. There we are. And we are done now with the leaky ReLU. All right, let's not forget the comma and let's move on to the next module. So the next module is going to be another convolution. Rest assured, we'll get many convolutions as we got many inverse convolutions. So we have a long way to go before making the architecture. So let's do it. Let's add this second convolution, nn.conv2d. There it is, and let's specify the arguments. So now you understand clearly the logic. The input of this new convolution is the output of the previous convolution, and therefore it is going to be the 64 feature maps. And now we need to choose an output. So since it's actually the inverse operation as the previous one, which was an inverse convolution, well, this time we're not going to reduce the number of feature maps each time for each new convolution. As you might have guessed, we're going to do the exact opposite. We're going to increase, and more specifically multiply by 2, the number of feature maps in each new convolution. Therefore, the size of the outputs here, that is the new number of feature maps we're getting as the output of this new convolution, is going to be 128. There we go. I think now you can almost finish it yourself, but we never know. Please stay with me. Then we're going to choose a size of 4 for the kernel, a stride of 2, a padding of 1, and no bias. Bias equals false. All right. Second convolution done. Perfect. Next step. Next step, as I just gave you a hint, is to apply a batch normalization. To batch normalize each of the 128 new feature maps. And so that's exactly the same as before. We're going to take our NN module, then dot, and then we're going to apply a batch norm 2D. And since we're batch normalizing the 128 feature maps, well, we exactly need to input 128. Exactly like before, no new mystery, comma, next step. All right, and now that's going to be the same. We're going to apply a new leaky ReLU. So I'm copying this. I am pasting it right here. And good news, we have the exact same arguments. We don't have to replace anything. We choose a slope of 0.2 and in place equals true. Next step. The next step, as you might guess, and I strongly recommend to play this game to try to type the next module in the architecture before me. The next module is going to be nn dot and a new convolution, of course, conv2d. Parenthesis. And now, of course, you guess what we're going to input and what we're going to output. We're going to input what was output by the previous convolution, which was 128 feature maps. So that becomes the new input of this new convolution. And for the output, well, we increase this time the number of feature maps. We multiply it by 2. So we're going to get the new output of 256 feature maps. All right. And then again, we choose a kernel of size 4, a stride of 2, and a padding of 1. And again, no, absolutely no bias. Bias equals false. Perfect. Comma, next step. The next step is to, guess what? Well, to apply a batch normalization. So we take our nn module dot batch norm 2d, and as argument, we're going to input the number of new feature maps that we got and that we want to batch normalize. And since what we got is 256 new feature maps, well, we're going to input here 256 to batch normalize these new 256 feature maps. Perfect. Next step, the leaky ReLU again. So nn.leaky ReLU, there it is. And that's the same. I don't know why I'm typing this again. I just need to copy and paste it. And there we go. Now another convolution again. So this time, let's not miss it and copy this, copy, paste. So this time we have 256 feature maps for the input, and we double it for the output. So we get 512 new feature maps in the output of this new convolution. And then same, a kernel size of 4, a stride of 2, and a padding of 1 and no bias. Great. Then our batch norm again. I'm copying this. I'm pasting it just below. I am not forgetting to replace the 256 previous feature maps by the new 512 new feature maps that we have to batch norm. Then we apply our leaky relu with the same parameters. So I just need to copy this, paste it here. I hope you are doing all this faster than me. All right, then almost over. We have one final convolution to add. This is the last one. I'm pasting it here. And so we're gonna get now 512 feature maps for the input. And now the question is, since this is the last convolution, what is going to be the output? Please don't answer 1024. We're done with the convolutions here. We stop playing the game of doubling the feature maps. No, this time we have to specify the final output of, therefore, the discriminator. And so if you understood the role of the discriminator, you should be able to guess the output here. Well, I'm going to tell you right now, it is actually 1. Why 1? That's because the discriminator is returning a discriminating number, a number between 0 and 1. So that's a simple vector of one dimension containing this number. And therefore, that's why we have a 1 here. And then just a little trap, you cannot really guess that, but we're going to keep a kernel size of 4, but then we're going to choose a stride of 1 and a padding of 0. And then that's the same, no bias. All right, we're almost done. We have one final thing to do for this architecture. If you look at what we did for the generator, well, you can see that after the last inverse convolution, well, we applied an activation function, again to break the linearity. And we're going to do the same for the discriminator, but this time it's not going to be a hyperbolic tangent. According to you, what is it going to be? It's actually a very classic activation function to use at the end of a neural network. It is the sigmoid function. And if you went deep into the theory of the deep convolutional GANs, and especially the part related to the discriminator, well, you would understand that the sigmoid function is the best choice because it returns some values between 0 and 1, and for the discriminator, we actually want to be between 0 and 1. Why is that? Well, the answer of that question is in the name of the discriminator. It's for a discriminating reason. The principle of the discriminator is that 0 corresponds to the rejection of the image, and 1 corresponds to the acceptance of the image. So 0 means we reject the image, and 1 means we accept the image. Therefore, the name discriminator, and so basically we want to be between 0 and 1 to do some discrimination. And that's why the output is actually a value between 0 and 1, because then using a classic threshold technique, well, for the values below 0.5, we will consider it as 0, so we will reject the image, and for the values above 0.5, we will consider it as 1, and we will accept the image. So that's very important to understand, and therefore the sigmoid function that not only breaks the linearity but also returns a value between 0 and 1 is the optimal choice for the activation function at the level of the output of the discriminator. Alright, so if you're convinced, we're going to get our NN module, and then dot, and then we get our sigmoid activation function. So it's an object of the sigmoid class, which will represent the sigmoid activation function itself, and we don't have any argument to input. So congratulations, you are done with the architecture of the second brain you have to create for our DC GANs. So now our DC GANs have the two brains. Let's make the forward function to propagate the signal inside the second brain. We'll make it in the next tutorial, and until then, enjoy computer vision.